Hola, ¿cómo están? My name's Dora, and we're going to school today. I'm looking for Boots. Can you help me? Great! I think he's in the cafeteria. Whoa, hey Boots!
Hey Dora, are you ready for the physics final today?
Okay, that's today? I'm not ready. Can you help me get ready for my final? Bueno! Let's go to the flex area. Hey, we good. Did y'all know that the physics final is today?
Yes, did you not?
No, can y'all help me?
Sure, what do you need help on?
I need an overview on magnetism.
Of course.
So all magnets have polarity and always consist of two poles, north and south. The poles are the points where the magnetic field lines begin and end. Also, magnetic poles with like charges, for example, if they both had positive charges, then they repel, whereas unlike poles attract. Now, a magnetic field is the space around a magnet over which the magnetic force exists. Here are some magnetic field lines to show you the relationship. So for a single magnet, the magnetic field lines look like this, and for a pair of magnets, they look like this. The magnetic field is stronger when there are more field lines, are most concentrated at the poles, and is measured in Teslas. Oh, and don't forget, field lines will always point from north to south.
Okay, I'll try not to, but can I ask a question?
Sure.
Okay, so if a magnetic field was around a current carrying wire, what would its orientation be and what is its presence?
Well,
A current carrying wire feels a force in the presence of an external magnetic field. A current that moves in a straight wire produces a magnetic field surrounding the wire. The magnetic field lines are concentric circles in planes perpendicular to the wire, and the strength is proportional to the current and inversely proportional to the distance from the center of the wire. A current carrying wire feels a force in the presence of an external magnetic field.
What about electromagnets?
well,
Electromagnets are devices that use electric currents to produce a concentrated magnetic field. Different factors affect the strength of an electromagnet. The greater current and number of loops create more strength. Also, the type of metal, voltage of the battery, and size of the wire also affect the strength. Electromagnetic induction, on the other hand, is when a conductor placed in a moving field or moving through a stationary field produces a voltage across the conductor and induces an electric current. Oh, one last thing. The magnetic field on a moving charge is perpendicular to the magnetic field in a velocity according to the right-hand rule. The magnetic force will also bend the path into a circle if the charge remains in a uniform field.
Wow, was that it?
no, you still got a while to go. Here, take this map. It will take you to your next topic.
Gracias. I cannot wait to learn again. Where should we go now? Should we go to the courtyard, bridge, hallway, or the library? Did you say the bridge? Okay, vámonos. Here we are at the bridge. What a beautiful scenery.
Boo!
Whoa!
Whoa there, where do you think you're going?
I'm trying to get to room 313 for my physics final, but I barely know anything.
Well, if you want to get past me, you're going to have to answer some questions about modern physics.
I'll try.
So there's four forces: strong, nuclear, weak nuclear, gravitational, and magnetic. So strong nuclear is the strongest of all four of them, and it has the shortest range, and it holds the nuclei together. Weak nuclear is responsible for radioactive decay, and gravitational force is the force that attracts any objects with mass. So the Earth attracts us to the ground, and then there's always a gravitational pull between us, even though we can't feel it. And then magnetic, there's an attraction or repulsion between particles that arise from electrical charge. So from strongest to weakest, it goes strong nuclear force, electromagnetic force, weak nuclear, and then gravitational. The next thing you have to learn is E equals mc squared. So E is for energy, m is for mass, c is the speed of light, which is 3 times 10 to the 8th power meters per second. So there's an equation or problem right here, and we have to find E. So m is 0.5 kilograms and c is the speed of light. E equals 0.5 times 3 times 10 to the 8th squared. And then E equals 0.5 times 9 times 10 to the 16th, because you square it, so it turns into that. And then once you multiply that out, you get as a final answer E equals 4.5 times 10 to the 16th. Okay, so now there's nuclear physics can be applied to almost anything. So now we have to explain MRI, CT scans, and aurora borealis. So the main thing is that many things such as smoke and metal detectors and many medical purposes like MRI and CT scans are used in nuclear physics. The protons in the magnetic field have one of two energies with their own intrinsic spin, which show off differently in MRI. So without radiation, the machine sends out basically it's a magnet and it pulls out and you can see a picture of your leg without using radiation. And then nuclear physics applies CT scans in that many x-rays are taken from every angle around a patient's body with a computer measuring the resistance of the x-ray waves through the bone and tissues of the patient's body, creating a cross-section image that is more detailed than a normal x-ray. So the machine spins around and is basically like an MRI, and it catches all of your bone, tissue, and everything else. And then the Heisenberg uncertainty principle, which you can measure a particle's position with increased accuracy, and then the act of observing a particle changes in velocity in unpredictable ways. So electrons are a prime example. Instead of giving a specific place for model, modern physics models put them in a orbital based on likelihood of different locations. So before it used to be a picture of rings, now it's a cloud, as they figured out that you can't know the exact location of electrons. And then assuming that the electrons exist in all the places simultaneously or in a superposition, allowing scientists to study atoms without knowing the exact location of its particles. And then the final thing you need to know is Schrödinger's cat. And it's a thought experiment developed to explain the principle of quantum superposition, and developed because quantum physics has random and unobservable phenomenon like Newtonian physics. And the idea is that you put a cat in a box and closed a vial of poison, a radioactive isotope, and a Jagandeep's counter. With the radioactive isotope decays, the Jagandeep's counter detects it and opens the poison, killing the cat. And the cat, rather than being definitely alive or dead, in its superposition, equally alive and dead at the same time, because we don't know exactly where it is. And then once you open the box and observe the cat, it is locked into place as being alive or dead. The very act of observing something changes its properties in fundamental ways.
Okay, so can I go now?
Wait, you have to answer one question to get through. Order the 4 forces that I told you from strongest to weakest.
Strong nuclear, electromagnetic, weak nuclear, and gravitational.
Fine, you can go through.
Where should we go now? Did you say the courtyard? Okay, let's go. Hey, Isabella.
Hey, what are you doing out here?
I'm getting ready for my physics final. Can you help me?
Sure, I'm an expert on thermal energy.
Heat is the amount of energy transferred between two objects with different temperatures. We use the equation heat change equals mass times specific heat times the change in temperature. How much heat is absorbed by 40 grams of copper when its temperature is raised from 30 degrees Celsius to 70 degrees Celsius? Well, copper equals 386 joules per kilogram Celsius, temperature is 40 degrees Celsius, and the mass is 40 grams. So that would be 0.04 kilograms. We multiply that all together to get 617.6 joules for the heat change. Temperature, the measure of the object's average kinetic energy, such as Fahrenheit, Celsius, or Kelvin. Thermal energy is energy that comes from heat that is generated by the movement of small particles within an object. So the faster these particles move, the more heat is generated. Thermal equilibrium occurs when the average kinetic energy of the atoms and molecules are the same. Heat will transfer until two objects with different initial temperatures will become equal with the same temperature. Kinetic theory of matter. explains the behavior of solids, liquids, and gases. All matter is made up of extremely small particles such as atoms, molecules, or ions. All particles of matter are in constant random motion. The first law of thermodynamics is the net heat put into a system and is equal to the change in internal energy of the system plus the work done by the system. So Q equals U plus W is the heat added to a system equals the increase in internal energy plus the work done. The second law of thermodynamics is a natural process that goes in a direction that maintains or increases the total entropy of the universe. Entropy is the measure of disorder. The more entropy, the higher the temperature. Kinetic theory explains the behavior of solids, liquids, and gases. All particles of matter are in constant random motion. We don't observe the movement directly, but we can measure it indirectly. Pressure and temperature, macroscopic, are indicators of particle movement, which is microscopic.
Thank you, adios. Where should we go now? Did you say the library? Okay, let's go.